This is our last video on how to represent variables. We are going to cover quantitative variables and we're going to finish up how to represent them numerically, and I also have one more type of graph to show you. The data we're going to be using for this example comes from the McDonald's website. They actually have a nutrition calculator you can use to see how many calories, how many grams of fat, etc. are in all of their meals. So I went in and found the amount of fat in 11 of their burgers and sandwiches. This is listed in grams. Okay, so to get started, what I want you to do is just make a simple stem and leaf plot using this data and include a key. So pause the video and do that now. Okay, so here's my stem and leaf plot. You can use any number you want in the key. I did 2 line 5 equals 25 grams of fat. And we can see that this is very symmetric. Now I didn't do every single sandwich. There were 2 that I clicked on and it said 0 grams of fat, and I feel like that's wrong. Now, in the last video, we learned how to describe a distribution using shape, center, variability, and outliers, which you either remember by those 4 words or the handy-dandy acronym VSCO. When we're talking about center, last time I just said, tell me about where the center is, and you'd say around 80 to 90 minutes, or here you'd say around 20-ish grams of fat. In this video, we want to find a specific number that we can give as a center instead of just saying the center is around blank. So there's 2 different numbers you can use to explain where the center is, or at least 2 that we're going to use in this class. Those 2 numbers are the mean and the median. Now you've likely seen these before. The mean of a data set can be thought of as the balance point. For example, if I have these 2 distributions, the symmetric one, if I'm trying to balance it, like imagine this is a ball I'm trying to balance it on, so I don't want it to, tip. If I want to balance this distribution, I'm going to have to line it up so that the tallest part of the distribution is right above the ball. Whereas this distribution is skewed, if I center it so that the ball is right underneath the tallest part, it's probably going to tip off the ball this way. So I need to move it a little bit this way so that I can balance it. So the mean is probably about there. Now, of course, there is a way to calculate the mean other than just imagining a distribution and figuring out where it would balance. And you've done this before. To calculate the mean, you add up all the values in the data set and you divide by the number of values. So I'll just write the first couple steps. So 9 plus 13 plus 16 plus yada yada yada. All over, there are 11 data points, and we'll just calculate that real quick. So I got 24.55 grams. Now you've likely done that when calculating your average for a class. Maybe you add up all your test scores and divide by the number of tests you've taken. That's pretty familiar to us. Try to avoid calling it average. Sometimes the word average could also mean median. So just call it the mean. No, I am not saying meme, although there will be plenty of memes in these videos. I'm saying mean. Okay, the median is the middle of the data set. So to find the median, we just have to count the data points until we find what's at the middle. Now when you learned how to do this, you might have learned to cross off numbers. That's at least how I learned to do it. So we cross off the smallest, cross off the biggest. Next smallest, next biggest. Small, big, small, big, small, big. Here's our median, 25. Funniest number. All right, so that's not that different than the mean. Just a quick side note, if you have an even number of data points, you'd be crossing things off like this: lowest, highest, lowest, highest, lowest, highest, and then there's nothing. You would just find the average of these 2 numbers. The median would be 16.5 in this case. In the burger example, we had an odd number, so that didn't happen, but just a heads up. Okay, now what I want you to picture is McDonald's adds a horrendous triple cheeseburger that has 99 grams of fat. Don't actually picture what that would look like. It's gross. Without doing any calculations, can you picture what would happen to the mean and the median when we add in this 99-gram sandwich to our stem and leaf plot? Pause the video, try to visualize that. Okay, here was our stem and leaf plot before. Here's with the 99-gram sandwich. It does not even fit on my screen. Okay, now before, the median was right here, and the mean was at 24, about the same spot. When we add in one more number to our data set, imagine crossing off lower, upper, lower, upper, lower, upper, we would end up with these two values, and we'd have to find the average of them to get the median. Halfway between 25 and 29 is 27, so the median goes up to 27. So that's how the median changes. The mean, however, is going to change quite a bit. Adding in a 99 here is going to drastically change the mean. I calculated it so you don't have to. The new mean is 30.75. Remember the one before was 24.55. So the median increased by 2 grams and the mean increased by about 6. Now, is that a big difference? We're talking grams of fat, maybe not. But it is important to note that the mean moved more than the median when we added in this large outlier. Now that's always going to happen. If you have a symmetric distribution and then you throw in one outlier far to the right, the median will only move a tiny bit. It might not even move at all. If you have several values in a row that are all the same, it probably won't move. The mean, however, gets dragged out towards that outlier. So where the median might only move a little bit or not at all, the mean will get dragged out towards the outlier. And of course that's true in the other direction as well. If we put an outlier way off to the left, the median might move a tiny bit to the left, the mean would move dramatically to the left. Now we actually have a word for this. The median is resistant to the outliers, and the mean is not resistant to outliers. These are really important vocab words in statistics. You can kind of think of this as like peer pressure in middle school. Most middle schoolers are not resistant to peer pressure. If they get a force over here exerting peer pressure on them, they're going to move towards the force. They're not resistant, just like the mean is not resistant to those outliers saying, come out this way, get bigger, get smaller. Whereas the median is more of a middle schooler who doesn't care what people think of him. Very rare. Now let's go back to thinking about describing. When we were describing a distribution, one of the things we had to mention was outliers. And in the last video I said, just mention any points that seem strange or that don't fit the pattern. But now we need to figure out, how do we actually tell if a data point is an outlier? The 99 grams, I'm willing to bet, is an outlier. But what about a sandwich that has 59 grams? That's not going to be that far away on the distribution. That might not be an outlier. We need a clear-cut rule for figuring out when a data point is and is not an outlier. So that's what we're going to do next. The first thing we need to find are the quartiles. Quartile 1 and quartile 3. Quartile 1 is basically the median of the lower half of the data, and quartile 3 is essentially the median of the upper half of the data. So we're going to go back to that stem and leaf plot that we made. And let's start by focusing on just the lower half of the data, so everything below our median of 25. Okay, so we're just focusing on the lower half. We're going to cross things off to find the middle. So lower, upper, there we go. 16 is our first quartile. Now we can do a similar thing with the upper half. So the median was 25, so the upper half would be everything above the median. Upper, lower, there's the median of the upper half. That's our Q3. Quartile 1 was 16, quartile 3 was 33. Now these quartiles, along with a couple other pieces of information, actually give us what we call the 5-number summary. So we have 2 of the 5 numbers. The other numbers we need are the minimum, which in this case was 9, the maximum, which in this case was 40, and then the median, which would go in here. I didn't really save myself enough space, which was 25. These are called the 5-number summary. We can represent these 5 numbers graphically, and before we get to the rule for outliers, I think we should do that because it's going to help us visualize where the outliers might be. So if you flip the page, if you're using the guided notes, there is a scale here, and we're going to use this to mark out where the 5-number summary is. So the minimum is the first number of the 5-number summary, that's 9, so I'm just going to put a line about where 9 is. Q1 was 16, so that's here. Something like that. The median was 25, that's here. The Q3 was 33. Maximum was 40. Okay, now that doesn't look very good. It's hard to see, so what we're going to do is put a box that starts at Q1 and goes to Q3, and then connect these with some lines. If you would like, you can label. We have min, Q1, median, Q3, and max. This is called a box plot. It's basically a visual representation of the 5-number summary. It's really important when you draw a box plot that you do it on a scale. Let's say this is what our distribution looked like. If it was drawn on a scale, we'd be able to say, 50% of the data is between these two numbers, and 25% of the data is between these two numbers. You can kind of use that to figure out what the distribution would look like if we were to make a dot plot. So if we were to line up an axis right underneath this, we know that 25% of the data is packed in this little tiny space from here to here. So there's probably very tall stacks of dots there. 25% of the data is here. We don't know exactly what it looks like, but we know that it's a bit more spread out. 25% of the data goes all the way out to here, so we don't know what it looks like, but we know that it's even more spread out. And we can kind of use this to figure out, oh, it's probably going to be somewhat right skewed. That's why it's really important that you do your graph on a axis, so it's to scale. Anyway, the point of all this was we were trying to figure out how we determine where outliers are. So here's the rule for outliers. Start by finding the interquartile range. The interquartile range is Q3 minus Q1. So Q3 minus Q1 in this case was 33 minus 16, that's 17. Next, we do IQR times 1.5. So for us, that's 17 times 1.5, which is 25.5. Then what you do is you do Q3 plus that number and Q1 minus that number. These are the upper and lower limits. Anything above 58 is an outlier. Anything below negative 9.5 is an outlier. I don't know of any sandwiches that are going to have negative grams of fat, like you eat them and they burn fat, but it's possible we might see a sandwich that's larger than 58. Based on this cutoff, we can definitely say that none of these data points are going to count as an outlier. Now the question was, what about 58? So let's imagine we're back to our original data set, but with the 58 added. What we're going to do is find the new median. You probably know what's going to happen here. Upper, lower, and this time we have an even number of data sets, so we get to 5 and 9, which means our median is going to be right in between those. It's 27. Just like when we talked about the 99 sandwich, the 58 is going to do the same thing to the median. It's going to move it just up slightly. Okay, now you don't have to recreate the stem plot, just pause the video and use my drawing, figure out Q1 and Q3. Okay, now the 25 and the 29 are not the median, so we have to include those in the upper and lower halves. So I've done Q1 already. 25 is our upper, 9 is our lower, so we cross those out. Now we have an even number of data points in our lower half, so our Q1 is going to end up being halfway between the 6 and the 8, so 17. Now I'm going to do the same thing for Q3, lower, upper, halfway between 33 and 36, 34.5. So the moral of the story is never include the median when you're calculating Q1 and Q3. Find the median, forget it's there, and then calculate Q1 and Q3. Pause the video and see if you can apply the IQR times 1.5 rule to see if 58 counts as an outlier. Alright, our IQR is 17.5 times 1.5 gives us 26.25. We add that to Q3 and we subtract it from Q1. So the upper limit for outliers is 60.75, the lower limit is negative 9.25. It looks like 58 is not an outlier. So it's comfortably in our limits. Now just a quick side note about box plots. Any data point that's an outlier will show up as a star or a circle or a dot on a box plot. So now thinking back to describing a distribution, two of the things we have to describe about a distribution are center and variability. Let's think about two different scenarios, a symmetric distribution and a skewed distribution. If the distribution is skewed, using the mean as a measure of center is a little bit misleading because the mean gets dragged out towards the outlier. So if you have a skewed distribution, you should use the median to describe the center. Simply because the mean is not resistant to those outliers, so the median is going to give you a better representation of the true center. If the distribution is symmetric, go ahead and use the mean. In general, these are the different measures of center you should use for symmetric and for skewed distributions. Now for variability, if you're using the median to describe center, just go ahead and use the 5-number summary to describe variability. The 5-number summary does include the median as one of the 5 numbers, and it gives you a really good idea of how spread out the data is by telling you 25% of the data is from here to here, 25 is from here to here, 25 from here to here. It's a good measurement of variability if you're using the median as your center. Now, if the distribution is symmetric and we're using the mean, the 5-number summary doesn't really make sense. We need a different measure of variability if our center is a mean. So we're going to use a smaller data set here because we're going to do some calculations by hand and I don't want it to be too painful. I found 5 different iced coffee drinks from McDonald's and recorded the amount of fat in each of those drinks. What I'd like you to do is fill out this table using these values. So you'll put the values here. The first column that you have to fill out is the distance from the mean, so you'll also have to calculate the mean of these 5 numbers. Pause the video and fill out as much of the table as you can on your own. Okay, the mean of these 5 numbers is 12.4 grams, so what I did is for each value, I did the value minus the mean. Now I know that distance in other math classes is often given as a positive number no matter what. However, in statistics, we often want to leave distance from the mean as a negative number to help us recognize that a data point is below the mean. So I know that distance is often positive, but in this case, we're going to leave it as negative. So 6, 11, and 10 were all values below the mean, and 17 and 18 were above the mean. Now, I don't know if you did this, probably not, because I didn't ask you to, but if you add up all these numbers, you get 0, which makes sense. The mean is the balance point, so the distances from the means are basically all going to cancel out. Now, what we're trying to do is find one number that can measure the spread or the variability of our distribution. So it can't just be the sum of these distances because that's 0. And that doesn't really tell us how spread out the distribution is. That's why I had you square all those values, because squaring all of them is going to make them all positive. If we add all of these up, that has given us the sum of the squared distances from the mean. To find the average of all of those, I divide by 5. This number is called the variance. In this case, it's 20.24 grams squared. It's telling us that on average, most of these data points are 20.24 grams squared away from the mean. Now, what is a squared gram of fat? I don't know. It doesn't really make sense. So the average we calculated is the average of the squared distances from the mean. If we want to find the average distance from the mean instead of the squared distance, all we have to do is square root that number we got. I get 4.5 grams. This number is called the standard deviation, and it's the best measure of variability if you're using the mean as your center. Now, if you're looking at the formula sheet for AP Statistics, they do give you the formula for mean over here. It's the sum of all the x values divided by the number of values, and they give you the equation for standard deviation here. Standard deviation is S. Now you'll notice they're dividing by n minus 1. We divided by n. For right now, don't worry too much about that. You'll almost never have to calculate standard deviation by hand. I'm actually going to make a separate video on how to use your calculator to find the mean, the 5-number summary, the standard deviation, and how to make box plots and histograms. So you can go watch that video if you want to see how to do this on your calculator. I'm guessing that most statistics teachers will not make you do this calculation by hand more than a handful of times. So let's go back to our summary. If you're using the mean as a measure of center, you should use the standard deviation as your measure of variability. When you're describing a distribution, start with shape. And once you've described the shape, make a call on which measure of center you're going to use and which measure of variability you're going to use. When it's time to describe outliers, you can use the IQR times 1.5 rule to determine if anything is actually an outlier instead of just saying it looks like an outlier. As I mentioned in the last couple videos, it's really important that we're describing data the same way. So I know that a lot of the stuff in the last couple videos has been a review for you, but it's really important if we're ever going to do inference in statistics and make big conclusions, we have to be talking about data the same way.